The word equilibrium has many meanings. The definitions that most closely apply to equilibrium in physics are balanced and unchanging. Specifically, an object in equilibrium has an unchanging or constant velocity. Since the velocity is constant, an object in equilibrium has zero acceleration. Remember that zero acceleration does not necessarily mean zero speed. If an object is moving at constant speed in a straight line, its acceleration is still zero. Newton's laws of motion apply whether or not an object is in equilibrium. Let's look at Newton's second law, where the acceleration of an object is equal to the vector sum of the forces acting on the object divided by the object's mass. Thus, for an object in equilibrium, the acceleration is equal to zero, which means the vector sum of forces acting on the object must also be zero. This is an equivalent way to define an object in equilibrium. The last relationship is a vector equation, which tells us the sum of the forces in both the x and y directions must be equal to zero. This allows us to write the equilibrium conditions in terms of the force components. We should note that these are the conditions for translational equilibrium. We are neglecting rotational motion, which we will study later on in the course. While the equations for equilibrium are simple, the problems we're going to solve can become quite involved. Below is a reasoning strategy for handling equilibrium problems. First, identify the objects in the physical system to which the translational equilibrium equations will be applied. Next, draw a free body diagram for each object in the system. Step 3. Choose a set of x and y axes for each object in the system and break the vectors in the free body diagram down into their x and y components. Step 4. Apply the equilibrium conditions by summing the x and y components of the forces on each object and set them equal to zero. And the final step, solve the system of equations obtained in the previous step for unknown quantities. The example below illustrates how these steps are followed. A box of mass m is at rest on an inclined plane, being held in place by a static friction force. The angle of the incline, theta, is as large as it can be such that the box remains stationary. Find an expression for the coefficient of static friction between the box and the plane. We begin by sketching a figure of the problem if one is not provided for us. Step 1. We have one object in our physical system, the box, and it is in equilibrium since it is not accelerating. Step 2. Draw the free body diagram for the box. We ask ourselves, what fundamental forces act on the box? We have the weight, which points straight downward. We also have the normal force, which is perpendicular to the surface, and the static friction force, which points up along the incline. Next, for step 3, we need to choose a convenient set of coordinate axes. Here we rotate our xy system so that the x-axis points down along the incline and the y-axis is perpendicular to the incline. Now we break the vectors in the free body diagram down into their x and y components. Since the normal force and the static friction force point along an axis direction, the weight is the only force we need to break down. Notice it has a y component in the negative y direction and an x component down the incline, which is in the positive x direction. And the angle between the weight vector and its y component is also equal to theta, the angle of the incline. Now that the vectors in our free body diagram have been resolved, we move on to step 4, which is to apply the equilibrium conditions by setting the sum of the forces both in the x and y directions equal to 0. Starting with the x direction, we have the x component of the weight in the positive x direction, and the maximum static friction force in the negative x direction. The sum of these forces must be equal to 0. Therefore, we see that the x component of the weight must be equal to the maximum static friction force. The x component of the weight is the opposite side to the angle in our weight vector triangle, and therefore equal to w sine theta. And we can always write the maximum static friction force as mu sub s times the normal force. This is our first relationship from the equilibrium conditions. Now we sum the forces in the y direction. We have the normal force which points along the positive y direction, and the y component of the weight which points along the negative y direction. The sum of these forces must be equal to 0. Therefore, we see that the normal force must be equal to the y component of the weight. The y component of the weight is the adjacent side to the angle in our weight triangle, and therefore equal to w cosine theta. This is our second relationship obtained from the equilibrium conditions. Now we are ready for our final step, step 5, which is to solve these relationships for the unknown quantity. Here, we wish to write the coefficient of static friction, mu sub s, in terms of the other variables. From the first expression, we see that mu sub s will be equal to w sine theta divided by the normal force. But from the second relationship, the normal force is equal to w cosine theta. We can make this substitution into the first expression and simplify our result for mu sub s. We see that the weight cancels, and we get our final result that mu sub s is just equal to tangent theta. This is reasonable as mu sub s has to be a unitless number. In this example, we have applied the equilibrium conditions to the case of a box being held in place by static friction. However, the systematic approach we've laid out here can be applied to any physical system in translational equilibrium.